Hello, this is Lecture 2. We're now looking at a brief introduction. Actually, I say brief, I mean a fairly comprehensive overview of the Arduino. We're going to be taking this lecture and the next lecture to give such an overview. So it's not exactly that brief, but compared to where we will be going with it, it is fairly brief. So this is an introduction to the Arduino. Now, part of what we're looking at in looking at the Arduino is we want to be able to consider what would be called appropriate microcontroller use. So part of what we're going to have you do is, as teams, we're going to have you explore appropriate microcontroller use, this subject. And we're going to do that by having you compare the microcontroller with some other device. So there are files. Each of you have been broken up into your teams, and there are files on Canvas under this directory that you can go and find that list advantages and disadvantages of the Arduino versus some other device. So I want you to distribute as teams. I want you to distribute the articles. I want you to then review the article that you have been assigned by your team. I want you to compare and contrast between the microcontroller and the other device that we're talking about. So examine the strengths and weaknesses of each, give an application of where one would be more effective than the other, and so forth for each of the devices, and then prepare a presentation for the scheduled date. So the date is listed on the class schedule, and so we'll see that. So prepare a presentation that your team will give for that. So some possible applications that you could consider. Would either of the devices that you're looking at be able to control, for example, the OBD2, so onboard diagnostics reader? So those are that's the computer module that's used in cars. So would the thing that you're trying to work with, the microcontroller or the other device, would those be useful in working with an OBD2 reader as a reader or as a controller? Can you read the values? Can you control the values? Those are the things you want to look at. What about whole home automation? Suppose we wanted to automate the home. So for example, you come in the door, there's a little keypad, you punch in a code, and it turns on your stereo. It turns on the lights in the bedroom. It dims the lights in the dining room. It turns on your microwave or whatever. There are different things like that. How effective? So obviously for something like this, you need something more than just the controller module itself. You would need other modules that would control the electricity to each of those devices. But assuming that you had those other devices, could you actually do whole home automation? So that would be something that you could look at as a possible application for your device or for the other device. What about a MIDI device? Could you use the microcontroller, that is something like an Arduino, to control a MIDI as a MIDI player? So MIDI being a musical instrument device driver. So, or what about MP3 player? Could it work as an MP3 player? Could the microcontroller be effective as a controller for a dishwasher or some other appliance like that? What about as a password cracker? Suppose you had a password that you needed to find. Could you use this to check passwords and to cycle through possible passwords? Would that be I mean, these are just some suggested applications. I'm not encouraging you to become a hacker and crack passwords. So as far as examples, what is an application for which the device is overkill? What is an application for which the device is inadequate? These are some things to look at in your presentation. So all of I've listed a number of things. You don't have to list all of them, but you don't have to deal with all of them, but it's important to keep these questions in mind as you go through and do the comparison. Having an application just makes the whole thing concrete. In terms of the comparisons, these are some of the things it will be asking you to look at. So what your group is going to be assigned something like one of these. The microcontroller versus an ASIC, the CPLD, DSP, FPGA, PLC, microprocessor. So microcontroller versus microprocessor. Okay, so these are all the different kinds. These are not all. These are a number of different kinds of other devices. ASIC, CPLD. These are other devices that employ some form of intelligence. And so the question is, can you use, why would you use a microcontroller versus an ASIC versus a CPLD or FPGA? Or perhaps an FPGA would be a better choice to use. So these are things you probably have not studied, and we're not going to study per se in this class. So I'm asking you to just do a little research and to investigate one versus the other. So part of it is you need to understand what each of these two things are. What is the microcontroller, and what is the ASIC or the PLC or whatever. What are those things? What are their capabilities? What are they good at? What are they not so good at? Those kinds of things. It's important to look. So in understanding this idea of what is appropriate microcontroller use, it's important for you to have a clear sense of the capabilities of each of these different devices. So your team is only going to be investigating one of these devices, and so you're just getting a little bit of exposure, but this exposure is giving you the opportunity to do some original research and to find out what is important regarding these various matters. Here are some topics that you need to look at in terms of your comparison or your contrast. So I want you to take of this list of 12 items. I want you to look at your device and the other device and compare and contrast regarding these issues. So I'm only asking you to do 5 of these, but 5 of them gives you a fairly rich set of issues to consider in terms of these comparisons. So first of all, computational power. Which one is actually able to crunch numbers more effectively? Okay, so is it the microcontroller, the PLC, or what? Ease of programming. Which one is easier to program? The microcontroller, like the Arduino, or the FPGA, which uses VHDL? Okay, so which one is easier to program? And why would you say it's easier? What is it about it that makes it easier? Okay, speed of operation. So that's similar to computational power, but not exactly. Here we're talking about just raw number crunching. Here we're talking about the speed of operation. So if you are sampling information, processing information, and then outputting information, that whole process is the full operation. How quick is the microcontroller, like the Arduino, compared to some other device, say a PLC or a CPLD or an ASIC? Which one is going to be more speedy that way? What about interrupts? How are the devices that you're working with effective at working with interrupts? So the idea of an interrupt is that is often referred to as asynchronous processing. The idea is that you have your system, your process running, and then you have a signal that comes in and says, I need you to do something right now. Stop what you're doing and pay attention to what's happening right now and do something right now with this. So that's the idea of an interrupt. How effective is the device you're considering? So the microcontroller or the other device, how effective are they at dealing with interrupts? Okay, ease of interfacing. So analog and digital interfacing. How easy is it to connect your device, each of the devices, for example, the microcontroller and the ASIC. How easy is it to connect an analog signal into that device, or a digital signal? How easy is it to connect in and actually be able to actually start getting data? The overall system cost. So, which one is more expensive, the microcontroller or the PLC or the microprocessor, like a computer? Which one is going to be the overall system cost? So, let's say you have the same task and both devices can do the same task. Which one is going to cost less to actually implement altogether? So if you have a microcontroller, you may not need a monitor with that microcontroller. So you wouldn't have the cost of a monitor, for example, and so forth. So this is just something to look at. Reconfiguration. So suppose you have it set up to do one task. How easy is it to tear it apart and put it back together for something else, to reconfigure? Okay. What about versatility? Which of the two situations would make it easier? So these two are actually somewhat related, but different. So this is actually reconfiguration, whereas versatility is reconfiguration means taking a device and making it into another purpose altogether. Versatility is which one has the widest variety of purposes that can be achieved. So in this case, reconfiguration, that's similar to, some of these others like ease of interfacing, but reconfiguration is more, I have two devices, they both can do this, they both can do two tasks. Let's say the same two tasks. How easy is it to reset both devices to do the other task? So it's set up to do one. How easy is it to reset it to do another task? Versatility is more which one can do the greatest variety of tasks. Okay. Number 9, communication with other devices. How easy is it to set up and start communicating with other devices? So let's say you have your microcontroller. You want it to communicate with, let's say, with Wi-Fi, or with you want it to communicate. You want it to read a GPS, or some other device. You want it to be able to receive, let's say, a signal from a remote controller, like a TV remote, so that you could use a remote controller to control that device. How easy is it to communicate with other devices? Okay, to set that up. What about timer or counter functions? How easy is it to set up each of the two devices to do timing or counting? And how accurate and reliable are those timing and counting functions? Okay, so that's an important thing. What about handling media? How effective is each of those devices at handling media? Audio, photos, movies. How effective or how powerful or capable is that device at handling media? Okay, so this last one basically says the overall time required, and by that it's meant the overall time required to set up a system for an application. So that's similar to reconfiguration, only this is like the first time around. The overall time required to set up a system. So here you have two applications and you're moving from one to another. This is like doing it the first time, setting it up the first time. What's required? How much effort or time is required to set up a system to do something the first time around? So these are just a number of ways that the two types of systems can be controlled. And so we're asking you to compare at least 5 of these things. So there's more than 5, and that's just to kind of help you see and to investigate a little with some direction what these two different types of devices that you're going to be working with are. So as a group, your groups are listed on Canvas, so you can go check out which group you're in, and based on that group, you can go and find out what devices to be looking at. So again, you'll be doing a presentation on all of this as a team, and so you'll be asked to investigate these things. And so notice I said at least 5 of these items, and the reason I said that is because you have 5 members in your team. If you have 6 members in your team, consider 6 of these things. Okay, so 6 of these. So for example, one of you would do ease of programming, one of you might do handling media, and so forth. So divide it up so that each of you has something significant to do as by way of comparison. And the thing is, this kind of information is available, and so I've included a number of documents on Canvas that talk about some of these differences, but there isn't a document that talks specifically in comparison of 2 things as concretely as all of this is here. And so you kind of have to read between the lines, you have to investigate. It's going to take a little bit of research on your part. So this is kind of like a research project that you will be doing, but instead of writing a long research paper and that kind of thing, you'll be making a presentation. That's the report. The report will be an oral report. And so we'll be looking to you. We'll actually be doing evaluations, oral report evaluations. We'll have each of you will evaluate other teams. Other teams will evaluate you, and so you will be given that opportunity both to present and to evaluate. So I believe it's important for every student to learn how to accurately communicate in regarding technical matters, and so this is one of the ways in which you will be asked to communicate. So it is this presentation. So I recommend using PowerPoint to do your presentations. So these are some issues to look at, Okay, now we're going to actually get in and do an Arduino overview. Part of what we're looking at here is not only, we're going to look at some of the finer details of the Arduino, but we're also going to, what we're doing here is kind of setting the stage for those presentations that you're going to give. So in other words, what exactly can an Arduino do? So in your comparison, you're asked to compare a microcontroller with, say, a PLC. So what we're going to be looking at now is a microcontroller, but a very specific microcontroller. Now, there are other microcontrollers. There are many different kinds of microcontrollers, just like there are a number of different varieties of Arduino. Arduino is an open source thing, which means that people can choose to implement it differently. So the basic Arduino has these functionalities. You have digital input and outputs. These are often referred to as general purpose inputs and outputs. The Arduino has a reset button that can be used to restart your program. There are analog input channels, digital input and output. There's ground, there's power. There's both 3.3 volts and 5 volts. It has a USB connection that allows you to program. It also has a power in case you want to use this thing independent of a personal computer. So in order to program it, you need to connect this up through USB to a personal computer that runs Mac Linux or Mac or Windows. And so if you want to use this system as a standalone system, you can, but it needs power. And so here's the power. You need 9 volts to go into here, and so you could also use a solar power if that provides the right voltage for you. So this is a basic layout of what we're working with. You have the digital ports over here. Each of these pins can be both digital in and digital out. Some of these have pulse width modulation. We'll talk about that in a little bit. There are ground connections, power, so you can this will actually supply power that you can use to power some of the devices that you're working with. So for example, if you have a sensor and your sensor needs power, you can get some power. So it's limited in the amount of power, but it can give you some power. You wouldn't want to use this power, for example, to drive a motor. It just doesn't have the oomph needed, and you don't want those kind of currents running through your circuit board, because you don't want to risk frying something. So, but if you want to power something that only requires small voltages, small current levels, then here's power available to you, both 3.3 volts and 5 volts. So 3.3 is common for CMOS devices. 5.5 volts is common for TTL type devices. Okay, so looking a little closer at some of these things, the Arduino also has what are called ICSP pins. So that is, you can upload code without a bootloader. I mean, that's interesting that you can do that. I personally don't understand why you would want to do that, since the IDE is so convenient to use. But anyway, you could do that. There is an LED that indicates that the Arduino is on. There's also a built-in LED that's accessible on pin 13, and it already has a pull-up resistor associated with it, so you don't have to worry about overdriving it with current. And there are other LEDs that indicate both transmission and reception of serial data. So those are these LEDs. So we have some other things that are going on. In addition, so part of what this Arduino can do is do communication. So the ICSP pins can be used for communication. Also, some of these digital pins, pin 0 and pin 1, can be used to do receiving and transmitting of data. So it's built in that way, and so there are functions that just access those pins directly to do some communication. So this is a layout of that. There are many compatibles for the Arduino. So the Arduino people made the Arduino open source, which means the basic functionality of the Arduino is defined by specifications. Anyone can build an Arduino that meets those specifications, and so as a result, people have built their own Arduino. So here are some example Arduinos, or compatible type Arduinos. So they offer, first of all, they have different cost, but they also, each of them offers additional capabilities. So capabilities in addition to the capabilities of the standard. So the standard gives basically like a minimum set of capabilities for the Arduino. But what some of these manufacturers do is they actually go beyond, and they actually introduce further functionality. So they do things a little bit differently. So all of the Arduinos need to have a USB port. But if you notice, this one has like a mini USB port. This one has what they call the D USB port. This one, instead of having a standard USB port, has these pins laid out like that, just like this one does. So it has a completely different USB type connection. So each of these chooses to do things a little bit differently. One thing that is clearly common is that they all have digital pins over here, analog pins over here, power pins over here, and so forth. So they all have it set up that way. They all have certain pins set up to be pulse width modulation pins, and so forth. Okay, so those are some of the things that they have in common. Each of these does things a little bit differently. So for example, the reset button over here is a little bit different than the reset button. All of them have a reset button. They don't all have them in the same place. So for example, the reset button for this one is over here, reset over here and here, like that. I'm not even sure where the reset button on this one is. But, well, anyway. So they just do things a little bit differently, and some of them, you know, have different costs, and so it's a buyer's market. There are a lot of options out there. In terms of shields, shields are things that you can connect up to your Arduino. So here's a stack of them. They're all nested, and each of these has a different functionality associated with it. And there are, this is the official shield list, so shieldlist.org. This is the official shield list of the Arduino shields. And so these are all the ones that have registered as shields. There are actually more than this. So for example, the Edu shield is not even listed in this list. And another one that you'll be using, an A to D shield, is not on this list. So you can make shields that are not on this list, and there are many that aren't. But even so, there are 317 different shields available from 125 different makers. So this was just updated here at the beginning of January 2014, and that's where we're at in the state of the number of shields. So these are the manufacturers. Notice that some of these, like Adafruit, makes 9 different shields. You know, some of these only make 1 shield, but some, you know, Seed Studio makes 14 different shields. So there are different shields, different purposes. The purposes vary widely as to what's available. Okay, the Arduino has what are called GPIO, General Purpose Input-Output pins. So back in my day, when I was learning microprocessors, they didn't have general purpose input-output pins. They had input pins and they had output pins. And you could do one or the other. But now, these things are smart. They can be used as input, they can be turned right around and be used as output, and so forth. They can go back and forth into their purposes. Okay, so each of the pins can be used as digital input or digital output. Each pin is uniquely assignable. In other words, you don't have to have them all as input and all as output. This one can be input, the next one output, and so forth. They all also have pull-up resistors that can be attached internally. I didn't say that here, but that's another thing. That's well, when we talk about interfacing, I'll talk about what a pull-up resistor is. But it's very handy to have a pull-up resistor right on board, so you don't have to introduce pull-up resistors. Analog or pulse width modulation output pins on pins 3, 5, 6, 9, 10, and 11. So there are 6. So this is the Arduino Uno. The Arduino Mega or Due or Leonardo or some of these other Arduinos. So they have even more of these pins. So the Arduino is a standard, and the Uno is one of it's probably the most commonly used Arduino. But there are other Arduinos more powerful than the Uno. So we choose the Uno because it's simple and cheap, and there are lots of shields designed for it. But some of the others can use some of the shields, and so for example, the Arduino Yun has the basic Arduino like an Uno on it, but it also has a Linux core on it. So it can be used as a personal computer if you hook up, and it's got connections for monitors and all. And so there are some really powerful Arduinos available. So but the basic one, and they all have general purpose input-output pins. So they can be used as input, they can be used as output. And there are also analog pins in 0 through 5 that can also be used not only as analog inputs, but they can be used as general purpose input-output digital pins. So some of the standards involve using some of the analog pins for communication. for serial communication. And so general purpose input-output pins. So in terms of digital inputs, there are different kinds of inputs. So this is an example of where we might have, for example, four different switches, each connected through pull-up resistors to 5 volts, and the other side of the switch is connected to ground. So this is an example where I can have, each of these are like basically represent push buttons, momentary contact push buttons, where you push the button down, and as long as you're holding it down, a connection is made. Okay, so and then we have these things called pull-up resistors. So the basic idea of a pull-up resistor is when this switch is open, this input connection goes through the resistor to 5 volts. Okay, so this signal here, since there's no place for the current to flow, this connection right here is going to be at 5 volts. Okay, so having this connection makes that worthwhile. When the push button is pushed, basically this point here is brought to ground. It's grounded. So it was at 5 volts, then you push the button. When you're pushing the button, you get ground. Okay, so that change can be detected by the Arduino and used to control something, to do something. Okay, so the idea of a pull-up resistor is when this thing is grounded, we don't have ground connected directly to 5 volts. That would not be good. Okay, that's called a short circuit, and that's likely to destroy your Arduino. Okay, you don't want that. So instead, what the resistor does is it provides resistance from 5 volts to ground, and so that limits the current that can flow through there. So that's something we need to do. So, but basically, this circuit that involves a switch and a resistor basically allows this signal to switch between 0 and 5 volts. And so you can't just do that with the switch itself. If you just try to connect up a switch to an input like this, it doesn't register the kind of voltage that's needed. So a digital input needs an input value of either 0 or 5. And this is a simple way of connecting up a switch to give that. Okay, so now internally to the Arduino, there are pull-up resistors, but it's always better. It's better if you can limit the current specifically with the resistor externally. So that is, if you choose to use the internal pull-up resistors, that can tend to heat the system up unnecessarily, and so it's better to have the heat outside the chip rather than inside the chip. So you can still use it, and it will still function properly, but it's tricky. It's a little tricky, and so you just have to, it's something that can be done. You just need to be careful with it. So these are discrete inputs. These can change. You know, anytime someone pushes one of these buttons, we get an input. Okay, but so that is communicating some information, but it's not just like sitting there giving communication. It is just, you know, every now and then it gets some values. And so this is very common for many different kinds of digital inputs. Another kind of digital input is where you actually want to communicate data. Okay, so here is an example. This is a luminosity sensor. Okay, and so between the Arduino and that sensor, we want to communicate. And so this uses the I2C or the I2C communication protocol. The I2C communication protocol is often referred to as a two-line protocol. So it uses an SCL and an SDA. So you can see here SCL and SDA. So it just needs those two wires. SCL, that's the clock. That tells it when the next bit is coming. And so this is a sensor, And as a sensor, it needs voltage and it needs ground. In this case, this sensor needs 3.3 volts. So here it says 3V3. That's actually the voltage is 3.3 volts. And so this sensor needs 3.3 volts and then ground. So that provides the ground. And then it also has these two signals that are connected to it. Okay, and so the communication, so the clock, so data is only transmitted as the clock pulses. Okay, and so in this case, it transmits when the pulse is high. When the pulse is when the clock pulse is low, that's basically time for the device to set up for the next bit. And so with this communication, you send a string of bits, bit 1 through bit n. So there's a start bit, and then there's a stop bit associated with this. And so this is how the communication protocol goes for the I2C. Okay, so the luminosity sensor is going to send a string of a string of bits, and those bits correspond to a number. So basically, what's going to happen is the Arduino will send like a command out to the sensor. The sensor then is going to take a reading, in this case of luminosity, and it's going to then send back data. Okay, it's going to send back data. It's going to take hold of the clock, and it's going to send data. So notice that this protocol can send data both ways. Okay, but and this uses digital inputs. In this case, the digital inputs are actually on the analog input. So as I mentioned, the analog input channels not only can be used to provide analog inputs to the system, but they can also be used as GPIO. In this case, they're used as digital information in the form of serial data coming into the system. So digital inputs with I2C. You can also do SPI. That's another form, very common form of serial communication. So again, serial communication is we're not sending some Captain Crunch over the line. We're sending bits of data, one after the other, serially. So here is a shield that is like a display shield, an LCD display or an LED display. No, I guess this is LCD. And so to print this pattern on the display, you need to send it data. And what I believe what this particular type of shield does is that each pixel in this display is sent. And I don't know if this is a color LCD or if it's a monochrome, which is single color. This looks like it's monochrome since it's only one, but it's hard to tell. Basically, the information for each bit is sent. The intensity is sent. So, for example, if this were a color LCD, each pixel has 3 color elements: red, green, and blue. Each of those colors has associated with it a number that tells it the intensity of that number. So red would have intensity 8 bits that would describe the intensity. 255 would mean full intensity, 0 would mean zero red. So every pixel then would have a value for red, green, and blue. And so 8 bits for red, 8 bits for blue, 8 bits for green. That's 24 bits that need to be sent for each pixel. Okay, for each pixel in this image. And so as you can see, there's a lot of communication, a lot of bits needing to get sent. And so the SPI communication is a common way of doing that. Serial Peripheral Interface is what that stands for. So I2C and SPI are the two common communication. So with the SPI, we have a master device and a slave device. So the master would be, for example, the Arduino, and the slave would be, for example, that LCD screen. So there's a clock signal, there's a master out, slave in signal, there's a master in, slave out signal. So this actually is a serial communication device, but it can do what is called duplex communication. That is, you can send data both directions simultaneously. Like the master can send data to the slave at the same time that the slave sends data to the master. Okay, so in some ways it's more efficient. And then there's what's called a slave select line that basically says, okay, we're going to use this device now. So every single SPI device is going to have a unique slave select line from the master. So this is more complicated than the I2C, which only requires 2 wires. But it is one of the standards that are used. So as you can see, there's a clock signal. So and notice here, SCK, that's actually the same as SCLK. So with these different devices, different manufacturers of devices will have slightly different acronyms for these different things. So here's SCK, which is the same as SCLK. Then we have MISO and MOSI, MOSI and MISO. Master out, slave in, master in, slave out. Okay, so this is the communication, the SPI communication. Analog inputs. So basically an analog input takes a continuous valued input signal from 0 to 5 volts, and it assigns, as it brings in the value, it assigns it an input value from 0 to 1027. So basically it's a 10-bit value. Okay, so if, for example, this were the input voltage that's coming in. So this signal, as a signal, is coming from some kind of sensor. And the value is changing with respect to time. So this axis here is time. And the value is changing with respect to time. And we want to keep track of that value as time goes on. So, for example, this could be this signal. This signal could be coming, for example, from a tachometer. A tachometer is used to measure the speed of rotation of something. So, for example, it could be the tachometer in your automobile. Okay, or it could be a speed sensor in cruise control. It tells you the actual speed of your vehicle, like a speedometer. Okay, and so that would somehow be converted from 0 to 5 volts. And notice the Arduino is expecting a signal from 0 to 5 volts. If you get over 5 volts, it basically truncates. If you get too high, you can actually fry your Arduino. So you need to be careful about going outside that range. But physically speaking, it's generally possible to apply a voltage that's larger than 5 volts. But you need to, and you need to be careful to make sure that doesn't happen. Inside the Arduino, when we grab a value, so this dashed line basically corresponds to what the value would be if we had grabbed it at that time. So and so you can see the shape of these two things look very similar to one another. Okay, this signal, for example, from here, can take on infinite number of values between 0 and 5. So you know, mathematically speaking, in any interval, there are infinite number of values. Okay, this can only take on 2 to the 10 number of values, anyway, a number between 0 and 1027. So that's the process of going from something that could take an infinite number of values to a finite number of values is called quantization. So there is that. And then there's also quantization in time. That is, I take a value here at this time, I take a value at that time. I may or may not be able to space them out uniformly, or I may not want to space them out uniformly. So the data, these blue values basically correspond to the values that come into the Arduino. And those are quantized both with respect to the value, which is from 0 to 1027, and also in time. In other words, I grab these at very specific values in time. I only know what the process is at the value at the time that I grab it. So when I grab a value at this point here, I can't tell, but just by looking at that value, whether the original signal was going up, going down, or it could be at the top, it could be, going up. I mean, it could be staying constant. You just don't know when you grab a value what's come before it, what's gone after it. You only know the value at that point. So you've thrown away a lot of data in this process of sampling. So this process is called sampling, and you're actually throwing away a lot of data. But hopefully you have enough data for it to be useful. And so we have issues. The issue of what's called aliasing that can arise when you sample. So aliasing is when you have a signal with certain frequencies, and if you have frequencies that are higher, that are too high for your sampling, then one frequency can appear to be another, and that's always an interesting phenomenon. So analog inputs are an important consideration. And that's an important feature of the microcontroller that we're working with. We can also have what are referred to as analog outputs. They're not truly analog. They're actually pulse width modulation. So pulse width modulation is a function that's defined in terms of the period and the duty cycle. So basically you get a sequence of pulses, okay, and that sequence of pulses has a period. That is, they start each. So for example, the distance from here to here is the same as the distance from here to here, and so forth. It repeats with a certain period. So the pulse width modulation is determined based on its period and its duty cycle. The duty cycle is basically the on time divided by the off time, and we express that in a percentage. Okay, so the on time, how long? So 100% duty cycle means that it's on 100% of the time. 0% duty cycle means it's on none of the time. And so it can be on anywhere from 0% to 100%. That's called the duty cycle. And so that is a characteristic of the pulse width modulation. So when you have a duty cycle, for example, of 50%, that means it's on half the time, off half the time. And so you have these pulses that are spaced like that. Okay, so that is the concept of pulse width modulation. Now, this idea of pulse width modulation can be used to vary, to provide, in a sense, a variable output, kind of like analog. So analog, it actually takes on all these values between, for example, 0 to 5 volts. but we can kind of simulate that using pulse width modulation. Video that kind of illustrates pulse width modulation. Over here, we have a plot of the pulse width modulated signal, and over here we would have, for example, an LED that's driven by a pulse width modulated signal. Okay, and so you can see how the pulse width modulation, notice we're increasing the duty cycle. Now the duty cycle is decreasing until it goes to all the way to 0. And here, as the duty cycle increases, basically the LED is on more of the time, and so it appears brighter. Okay, so, but notice that, that basically the LED is flashing, but it's flashing so fast that you can't see it flash. So that idea is very commonly used, for example, in movies. It's what makes a movie look like something is moving, right? You see one image, then the next image, you see it flashes another image. The next image is like the next step, and so it looks like there's this continuous motion when actually it's just a sequence of motions, and your eye integrates. It actually integrates like an integrator, like calculus. Yeah, really. But you don't need to understand how that works. The important thing is that your eye kind of averages between different things, and it smooths things out, and so it makes it look like the intensity is changing. The intensity actually is not changing. When it's on, when that LED is on, it's actually full on, and when it's off, it's full off. Okay, but in your eye sees it as being brighter because it sees it on more of the time, and that kind of puts more light into your eyes that gets integrated. So this is just showing the process of pulse width modulation and how it varies, and it can be used to provide what looks like an analog output. So this looks like I can vary the light intensity from 0 to full on, but the reality is that that it's not actually 0 to full on. It just appears to be that way because of the way our eye integrates that quantity. And this kind of thing can be used. So here we've shown it with an LED, and it's very well known that flashing lights, if they flash fast enough, cannot be detected by our eyes. So, for example, that's the principle of movies. That's the principle of fluorescent lights. All of the fluorescent lights flash at 60 cycles per second. 60 times per second they're flashing. But if we saw them flashing, it would drive us batty. We don't see them flashing. Actually, sometimes you can see them flashing, but you don't see them flashing, and so it doesn't bother you. In fact, instead, it just gives you the light that you need, right? This kind of principle can be used in other applications like motors, where, again, if you just send pulses like this, if you were, it's basically you're pulsing. You're just pushing the voltage into a motor, but you're not pushing it all the time, and so you can get like a reduced speed if you used a smaller duty cycle. If you used a full duty cycle, that would be like full speed and so forth. And so you can get like a proportional speed of a motor based on the duty cycle. So the speed of the motor would be proportional to the duty cycle. So full duty cycle, 100% duty cycle will give you full speed. 0% duty cycle will give you 0 speed. 50% duty cycle would give you a speed halfway between full speed and 0 speed, and so forth. So it's proportional. So it looks like it's analog. It looks like it's proportional, but it's actually being driven by a digital signal. So it's not truly analog, but it has some nice properties like analog. Now, so far what we've kind of focused on has been the hardware side of things. What do we actually connect up to this Arduino? But the bottom line is what we're working with this in terms of an embedded system is we need a system with intelligence, with brains. And so what we've primarily looked at are like the shields and things like that. That's all hardware. Those are connections that can be made in order to do certain things. But those connections do not do the things. We need intelligence. We need software to give us this. And so we have different kinds of software that can be used on the Arduino. We can develop software using the Arduino IDE. We can develop software using C or C++. And we can develop software using assembly language. So those are the 3 types of software we're going to be developing for the Arduino. We're going to develop all 3. Okay, so basically what these provide for us is the brains that go on within the Arduino. The Arduino itself and the connections do nothing. It can do nothing. You have to apply brains. You have to apply intelligence. The intelligence that we apply to the system is going to come in the form of software developed in one of these 3 platforms. And actually, they're all going to be developed within the Arduino IDE. The Arduino IDE, basically by itself, has a set of commands that can be used, but it's a very limited set. We can extend that set if we want to use C or C++. And if we use assembly language, then we can get other advantages. So here are some comparisons between the different types of software that we will be using. The Arduino IDE, C, C++, and assembly. Okay, so we have these different things that can be used to assess the various forms of software. So in terms of ease of development, the Arduino IDE is easy. It was purposely designed to be easy enough for artists to use. Okay, you don't have to be a PhD in electrical engineering to be able to use the Arduino IDE. Okay, an artist, someone who has a very low technical background, can use the Arduino IDE. A housewife who wants to design clothing that can flash or do something. That's the Arduino IDE. It's designed to be easy. Okay. C or C++ is of moderate complexity. Okay, now you can actually do pretty complicated things with C and C++, but in terms of the difficulty of programming, it's moderate. It's pretty moderate. It's not a horrible programming language. Okay, but it's moderate in terms of its ease of development. It's not as easy as the Arduino IDE. Arduino IDE is designed to be simple, and so with C, it's not as easy. So if you want to get into complicated things like pointers and address pointers and all those kinds of things, it can be pretty complicated. Or if you want to use malloc or alloc or any of those, there are complicated constructs that can be used within C or C++. Object-oriented stuff. You can get really complicated. It doesn't have to be that complicated, but you can get really complicated. So that's why I say moderate. Assembly language in general is pretty challenging, because in assembly you have to be intimately aware of the hardware and how the hardware functions. And so generally speaking, assembly language is challenging. So we will be getting into this, but just to let you know, in terms of these aspects, we go from easy to challenging. In terms of libraries, there are many libraries available for the Arduino IDE, and many of those are written in C and C++. So what is a library? The library is a collection of functions and tools, software functions that can be used to perform something. So for example, if you want to control a stepper motor is a motor that's designed to be able to take steps. But it turns out it's a fairly complicated process to get a stepper motor to step all the way around. It requires a particular sequence of turning. You have like 6 wires on some step motors. You turn this wire on, this one off, this one on, this one off, this one in the positive direction, this one in the negative direction, and there's the sequence of things that you need to do in order to get a step motor to turn. And then there are things called microstepping, where you can take very small steps, and that requires a very precise sequence of things to happen. Well, that sequence of steps has all been encapsulated into a library function. And so by calling that library, and by including that library, you can take advantage of those functions, and you, as a user, don't even have to understand really what's going on in order to use it. Okay, so those libraries is one of the things that makes the Arduino so attractive, is that there are many libraries available for all kinds of things, for looking at GPS, for using VGA audio, for doing MIDI functions, for all of these libraries have been developed, and so you can just use them. Well, it's not usually quite that easy. Sometimes it is that easy, but not always. Sometimes you kind of have to figure out how to use them, because some of these libraries, yes, they do solve the problem for you, but they're written by engineers, and engineers aren't always very good communicators. They're not always very good at documenting what they're doing. They're not always good at explaining some things. And so, sometimes you open up a new device and it's like, I don't even understand how to use this thing, even though I've just finished reading the directions, So, I mean, it's that kind of thing. So sometimes it's as easy as just using it. Sometimes you actually have to kind of play around with it to figure out what's actually happening. So, but the Arduino IDE and so many of the libraries are actually written in C and C++. The people who developed those libraries have done it that way. But they're available within the Arduino IDE, and the Arduino IDE itself actually has a whole set of libraries. And we're going to use some of those. For example, the serial library will allow us to do serial communications And we don't have to understand the library. We don't have to understand what it's doing. We can just use it. Okay. So the disadvantage with assembly is, as far as I'm aware, there are no libraries available for doing assembly language. So that is kind of a drag. So if you all are so inclined, perhaps you can design a library, a set of libraries to work with assembly language. It's possible that you could even make a little bit of money that way. Yes, even you, after taking this very class, could do that. Okay, well, anyway, speed. How does the Arduino IDE, if you have code written in Arduino IDE, how does that give you speed? Well, basically, it's slow. It's slow. Okay, by comparison. By comparison, it's slow. Now, because of the fact that you have a microprocessor running at 16 megahertz, it's not that, I mean, it doesn't seem that slow. It's certainly fast enough for many things, but by comparison, it's slow. If you have things written in C++, it's comparatively fast. You can get it quite fast. But when you write things in assembly language, it is as fast as possible. You can streamline it so that it is as fast as absolutely possible that machine can go. It's as fast as the machine can go. Okay, we're going to see an example here in just a bit, a comparison between some of these things, just to kind of give you an idea of how that works. Okay, the accessibility of processor features. So the processor has a whole long list of things that can be done with it. It has all kinds of capabilities. Okay, so the Arduino IDE is very limited in those processor features. It's very limited. Okay, so the thing is easy, but it's very limited. There are lots of things that your Arduino can do that you cannot access directly using the Arduino IDE. Okay, so very limited. Now, if there's a library that already does that, no problem, you're done. But if you're trying to develop something new, which may often be the case, and that's the kind of thing we're going to be emphasizing in this class, is to have you develop new things. Very limited. Okay, so there are certain things, for example, on your Arduino R3, the revision 3 of the Arduino Uno, built inside is a temperature sensor that allows you to measure the processor temperature. Okay. The Arduino IDE does not allow you to access that. Okay, so even though it's built into the system, the Arduino IDE will not allow you to access it. Now, could they add a function that allows it? Yes, they could. They just don't. So there it is. It sits. You can't use it. The counters, the timers on the Arduino IDE allow you to get 10-bit pulse width modulation, but you cannot do that using the standard Arduino IDE. You cannot use, so you're stuck with 8 bits of pulse width modulation, which is not that bad, but it is a limitation. Whereas most of all the accessibility features of the Arduino, most of them you can access using C or C++. Okay, you can. So, in fact, I don't even know what things you can't. I just know that in general, most of them you can access. Okay, so definitely more powerful. And finally, using assembly, you can access all possible processor features. Anything that's available that you can actually do, you can do using assembly language. So in terms of ease, Arduino IDE is definitely easy. In terms of power, the assembly is the most powerful. In terms of library, there are many libraries for the Arduino IDE, but in terms of speed, the assembly is as fast as possible. So there's a trade-off. Sometimes it's better to use the Arduino IDE because you can develop something quickly, but if what you need to do is to do something weird and fast, then assembly language is the way to go. So each has its strengths and weakness. Okay, so the Arduino IDE, free, nice, free software. You can download it from the website arduino.cc, and you can go there and download it. It's available for Mac, Windows, and Linux, so that's nice. You can just go and use it on any of these platforms. There's also, I believe, setup information. So if you download the information, download the software, it'll tell you how to set it up. There is a procedure, especially for Windows and Linux, about how to set it up to get it to use. For Mac, it's very straightforward, but for the others. Now, we have modified the Arduino IDE at New Mexico State. So I don't know of any other place that does this, but we had a couple of, Doctors Cook, Jonathan and Janine Cook, who figured out how to work the Arduino IDE so that you could do assembly. The Arduino IDE by itself does not do assembly language, but they figured out how to modify the Arduino IDE to be able to do assembly language. And so that's when we do assembly language, we're actually going to do it within the Arduino IDE based on the hacks that Doctors Cook came up with. And so the standard IDE that you download off the net will not do assembly language. So when it comes time to do assembly language, we will have to do a custom. Basically what they did is the Arduino IDE software is open source, so you can download the source code for that program. And so basically there was a very small modification that was required in order for the Arduino IDE to be able to read properly assembly language code. And that's all it was required. It could already do the compilation and the all of that to handle the assembly language code, but it just had no way of actually being able to read the code. And so the hack that they created was tweaking the IDE so that you can read assembly language code. And so we will use that when we come to that section of the working with the assembly language. So that is not your standard IDE distribution. We will work with the IDE, but it will be a modified version of it. Thanks for watching.